Alright, so we have some non-conducting sphere of uniform volume charge density. That's pretty cool. It's surrounded by a conducting spherical shell. So this is a conductor. The sphere has a charge of negative q in the... Okay, so negative q. Ooh. So this internal sphere here has a negative q, and the shell has 3q. So the entire shell has 3q. Would determine the charge on the outer surface of the shell. Okay, so because this is a non-conducting sphere, this part is non-conducting, which means there's no electric field in here. So to add up to 3q, there must be some charge on the inside q that basically balances this out, because there's no net electric there's no net charge if we draw an electric or a Gaussian surface in here, right? There would be no net electric flux, or no net charge. So these plus q and minus q have to cancel on the inside of this shell. So there must be a plus q on the inside, meaning that the answer is 2q, because we have the shell charge has to add up to 3, so the inside and the outside add up to 3. So that is part A. Alright, so we have next, using Gauss's law, derive an expression. So r is some distance from the center just outward. We don't know, it could be here, or it could be here or here, just any distance. It's just, this r is not constant. It's subject to change. Using Gauss's law, derive an expression from the distance so that r is less than big R. So we're going to be considering little r. This distance is going to be less than this internal sphere here. So we're going to write out Gauss's law. So we're going to do the surface integral of E dot dA. And if we kind of consider like a Gaussian sphere or whatever, then EA will be, or the surface integral will just be constant. So Q enclosed over epsilon naught. Okay, so then we have just, if we assume this electric field is constant with that Gaussian surface, we do E times 4 pi, and which R are we going to look at? We're going to look at the little r squared, because we're just trying to figure out the electric field inside of some tiny radius, not the radius out there. So this is tiny r squared. If it was outside big R, then it would only go up to R, and we would do big R squared. But it's less than, so we're just going up to this tiny r. And so it's going to be equal, and now we need to find this charge enclosed. So alright, to find the charge enclosed, we're going to do some arithmetic over to the side here. So the charge enclosed, Q, and is going to be the ratio of the volumes. So V is going to be the charge times the ratio of the volumes here. So V total. And so the chart, or the volume enclosed, is just the volume of the little r with respect to little r. So 4/3 pi little r cubed, and that's, I'm pretty sure that's on the formula sheet. And then 4/3 pi, and then to the total volume of this sphere is big R cubed. And so now you can see that these 4/3 and the pi's cancel, leaving that Q enclosed is now Q times little r cubed times, or over big R cubed. So we're going to go over here and write that. So it's going to be Q times little r cubed over big R cubed times epsilon naught. Epsilon naught. Alright. I think there's an epsilon naught. I'm not sure. I'm just gonna leave that end there. Alright, the magnitude of the electric field. Alright, oh wait, I gotta solve for E on this earlier problem, so let me quickly do that. Just divide both sides by 4 pi little r squared. So r squared, so 2, or an r squared will cancel, leaving Q r over 4 pi r cubed epsilon naught epsilon naught. There we go. Okay, so this electric field is at R equals R. So at the shell, it is 8 newtons per coulomb. So at that point, these ratios of the volumes are the exact same. So we can kind of skip this step right here and set, I'm gonna basically rewrite, just in case they were looking for it. Actually, I'm gonna go back and do this in blue. Just in case they were looking for all of the work here, I'll write it. So E dA is equal to Q enclosed over epsilon naught. But here, we know this is going to be 4 pi little r squared. E 4 pi little r squared. And this time, you don't have to do any of this. This is just equal to Q over epsilon naught. And so now if we solve for E here, so E is equal to Q over 4 pi r squared epsilon naught. And so if this is 8 at r is equal to 2r, so we're just going to kind of write 8 here, or r is equal to r. So this little r squared is just we're going to substitute big R here, right? So if this is r squared, and this is 8, when we double the r here, this is still going to be squared. And so instead of this being that, it's going to go to 2r squared. And so this is actually going to be a factor of 4, but it's 1 over. It's multiplied by 1 over 4. We're just substituting this back into it. So 8 times 1/4. And the units are in newtons per coulomb. So newtons per coulomb, and it's 2. And so that is part B. I guess I'll label my parts. So this is B and this is C. Alright. So I guess I'll do this one in yellow. So derive an expression for the absolute value. So we need to find the potential difference. Let's see. So the electric field is dV dx. So V would be equal to moving dt to the other side and integrating it. So the integral of E, sorry, not, this is x, not t, d, and then this is in terms of r, so we're going to do little r, E dot dr. And so then we can, what are we going to integrate from? Outer surface, so that's r, to the inner surface of the shell, that's 4r. 4r. So are we going to actually have to do some calculus? This is pretty cool. Alright. Let's see. So now we can start substituting. So we're going to say V is equal to the integral of r to 4r of, let's see. Okay, so we're going to start with the value for r. And so we're just going to do Q over 4 pi r squared epsilon naught dr. And then we can now pull out literally everything else because it's a constant, which is going to be Q over 4 pi epsilon naught. 4 pi epsilon naught times let's see here. Then what is the integral of 1 over r squared? Let's do some power roll over to the side. So r to the negative 2. We're going to add 1 to the exponent. So it's r, then negative 1, and then multiply. So it's going to be 1 over r. And then we're going to evaluate this from r to 4r. And then now I could just substitute in values. So that's q 4 pi epsilon naught Gonna draw a circle, and then times negative 1 over 4 4r. Let me put this closer. Negative 4. Oh wait, it's 1 over r, and so it's gonna be 1 over 4r. And then we're going to do minus a negative, so it's going to be plus 1 over r. And then we can get a common denominator. So multiply both sides by 4r. Or no, multiply both sides by 4. Yeah, and then we can right, so let's get a common denominator over here. Multiply both sides by 4 times 4. And so that would be negative 1 plus 4 is going to be not negative 3, positive 3 over 4r times and then I could actually 4 times 4 is 16, so 16 r times pi epsilon naught, and then there we go. Alright, and then this last little bit should be fairly easy. Just some graphs. So, let's see. We're going to find the electric field as a function of r. So, as the radius increases here, we have it's going to get closer and closer to 0 asymptotically. Or no, it's going to be a linear function because this is a linear function of r. Now, is the electric field positive or negative? It is negative because q is negative. So I'm gonna draw a roughly straight line, and then the second area between r and 4r is, let's see, that is proportional to, let's see, little r squared. Yeah, we did that over here on my mess of work. So this is going to approach 0 as a 1 over r squared. And then after 4r, it's going to have a positive electric field. Because the net charge is 3, and so it's going to jump up. And then we're going to go decrease again as a function of r squared, because then we could start treating it like a point particle. And then, let's see here, electric potential. And so the way I remember this is dV dx is equal to the electric potential, or the electric field in the x direction. So we have the graph of the electric field, and so we just integrate it. And so I know, so basically if you were in like a calculus class, there would be something like, hey, here's the graph of the derivative, find the f of x graph. And so this is a linear function, and so when you integrate a linear function, you get a quadratic. That's also a linear function. I don't know what that was. Something like that. And then, let's see here, this is a... So this is proportional to... So if this is a proportional to r, which is technically little r, and this is proportional to 1 over r squared, and this is proportional to 1 over r squared as well. Right? But this part is negative, so it's going to get more negative, but less so. So it's like that, because it's the negative 1 over r. I literally wrote that upside down. So it's going to decrease like that, and then at 4r, it's above the x-axis, so it's actually going to go up and decrease and and the voltage is going to get closer and closer to 0.